Jai Hind friends. In today's session, we will learn that how we can use available timers, counters in 8051 microcontroller. Since we all know that 8051 is a microcontroller, 8-bit microcontroller to be more precise, and it is having onboard timers and counters and interrupts, serial communication port and other peripherals like input output ports and all. So, if we are targeting to use timers and counters, then we must also took interrupts into our consideration, because practically whenever we are going to implement timers, interrupts play a very important role. So, we will see in today's session that along with the interrupts, how we can use timers and counters of 8051 microcontroller. So, first let me tell you something about the interrupts. An interrupt is an external or internal event that interrupts the microcontroller to inform it that device needs its services. As we know that in our project, we often combine several peripherals or several devices. We often interface these devices with our microcontroller, and at any moment of time, if any device needs any help, it wants to communicate certain message, or it wants to uh, tell the microcontroller that it is not working or it need any external additional help, then the device may send an request to the microcontroller. That request generally is known as interrupt request, and in return to that request, microcontroller execute a specific program that is often termed as interrupt service routine, or ISR, and that ISR is responsible to respond or to fulfill the demand or need of that peripheral device. So, in 8051 we are having 6 sources of interrupts. In some text you may find that 8051 microcontroller is having only 5 interrupt sources, but here I am talking about 6 interrupt sources because I am considering reset also as an interrupt. If you do not consider reset as an interrupt, then you can say that 8051 is having only 5 interrupt sources. So, I am showing you the interrupt vector table that is available inside the read only memory of 8051 microcontroller. We all know that in 8051 microcontroller there is 4 kilobyte of read only memory, and that is also known as flash memory. And inside this read only memory or ROM of 8051, uh, initial memory locations are reserved to store the interrupt service routines. So, here on my screen you can see that we are having 6 interrupt sources available. The interrupt sources are reset, external hardware interrupt, that is also termed as INT0, then timer 0 interrupt, and external hardware interrupt for that is also known as INT1, and timer 1 interrupt, and serial communication interrupt. So, whenever any of these interrupts occur in our system, then microcontroller forces its program counter to reload the address of these locations. For example, if a reset interrupt is occurring, then controller or the program control will be transferred at memory location 0000H, that is the very first or initial memory location available inside the ROM of 8051 microcontroller. Reset, you can compare or you can say that it is a type of non-maskable interrupt, and the reset pin is available inside the 8051 microcontroller IC at pin number 9. So, whenever we are sending any signal to pin number 9 to reset the microcontroller, and we mean by reset that we want to start the program execution since the beginning. So, whenever we are sending any signal to this reset pin, then program control will be transferred to memory location 0, and the program execution starts from memory location 0, that is the beginning of program. Similarly, in 8051 microcontroller pin IC, we are having 2 pins. These pins are available along with the port 3, These pins are responsible for handling the external interrupt sources. Like we can connect any button or any other peripheral to these pins, and if those peripherals are sending any signal, then microcontroller may be interrupted. So these pins are known as INT0 and INT1, and on the IC you can see that P3.2, that is pin number 12 of 8051 microcontroller, and P3.3, that is pin number 13 of 8051 microcontroller. These two pins are dedicated for external interrupts handling INT0 and INT1. So, if any interrupt has occurred at pin number 12 or port 3.2 pin, then program control will transfer at memory location 03, and if any interrupt has occurred at pin number 13 of our microcontroller, then program control will go at memory location 13H, 13H. Similarly, in case of timers, we are having two timers, 16-bit timers with our 8051 microcontroller, and if interrupt has occurred for timer 0, then program control will go at memory location 0BH, and similarly in the case of a timer 1 interrupt, the program the program control will go at 1BH memory location. And if we are performing serial communication with our 8051 microcontroller, then for handling the serial communication based interrupts or RI or TI process based interrupts, we have a memory location reserved for that ISR is 23H. Here, and one interesting fact that you can see, that for reset we are having only 4 memory locations, only 4 memory locations or 4 byte of space is available inside the ROM of 8051 to store the interrupt service routine for reset. But for other 5 interrupt sources like external interrupt 0 and 1, timer 0 and 1 interrupts, and serial communication interrupts, we are having 8-byte space inside the ROM. We can save the ISR or interrupt service routine for INT0 from memory location 0320A. These are the 8 bytes. So here we can see that we are having very limited and only 8-byte space to store the interrupt service routine for the 8051 microcontroller. It is often very difficult to store or to write such a short ISR or interrupt service routine, and we will see that how we can manage if we are having more than 8-byte long ISR if in our project, then how we can manage this interrupt vector table and ISR locations. To enable the interrupt, by default in 8051 microcontroller, all interrupts are disabled. So, if we are not enabling these interrupts deliberately, then we may not use these interrupts in our microcontroller. So, if we want to enable the interrupt, we need to take use of one of the SFR, that is a special function register, and one of the special function register is interrupt enable register, that is also known as IE register, is responsible for enabling or disabling the interrupts. So, here you can see the structure of IE register. IE register is 8-bit register, and inside this 8-bit register, D0 is reserved for external interrupt 0. ET0 means signifies that you want to enable or disable timer 0 interrupt, then you can write here at ET0. Similarly, EX1 for external interrupt 1 and ET1 for external timer 1 interrupt. ES for serial communication interrupt, RI or TI based interrupts. In case of 8051, ET2 is not available because timer 2 is a feature of 8052 microcontroller. So, if we are using 8052 microcontroller, then ET2 bit is available inside the IE register, and if we are using 8051 microcontroller, then ET2 is not available at all. So, you can say that these bit locations D6 and D5 are not used or may remain in don't care situation in case of 8051 microcontroller. The important bit is EA, that is the bit D7 or MSB of this IE register. This EA stands for enable all. So, the process of handling the interrupts with 8051 microcontroller is very simple. Suppose we want to enable external interrupt 0 and timer 1 interrupt in our application. So, what we can do first, we will write 1 at bit position D0 to enable the external interrupt 0. We will write 1 at ET1 position or ET1 bit to enable the timer 1 interrupt, and if we are not enabling EA, then these two interrupts will not be enabled. To enable the interrupt, any of the interrupt, one or many interrupt, we need to enable EA. You can consider this EA as a main switch or the MCB of your switchboard. So, if you want to turn on your fan, you are turning on any switch on your switchboard, but if MCB is not on or the main switch is not on, then your fan is not going to work or not going to be turned on. So, this is the method that first we will enable by writing 1 at the respective bit position. The corresponding interrupt will be enabled, and at the same time we will write 1 at the EA bit, or we will set this EA bit to 1, so that that interrupt must be enabled or may be enabled, and that may be used in our application. So, here this is the important point regarding the IE register of the interrupt 8051 microcontroller. The next thing, we are moving towards the timers. We will see when we will use timers, then we will use interrupt of those timers. Like if we are using timer 0, then we will use ET0 bit to enable the interrupt respective to timer 0, and if we are using timer 1, then we will use ET1 bit to enable the interrupt respective to timer 1. And at the same time we will make EA1, so that these interrupts may be enabled properly, and they can work perfectly in our system. Sorry. In 8051 microcontroller, we are having two timers, or you can say these are counter as well. So, actually there are only one device. That device can work as a timer, and that the same device can work as a counter also. So, in 8051 we are having two timer counters, or the timers, generally they are referred as timers. These timers are basically used to generate a time delay, and in most of our application there is a need to generate a time delay between two process or between two events, so that a proper synchronization must be ensured among the microcontroller and the peripherals, because microcontroller is always the fastest device in our system, and the peripherals are comparatively slower than the microcontroller. So, in order to make the synchronization between the peripherals and the microcontrollers, or in some another extent or another context, we can use a delay, or we must use delays. So, in order to generate delays in our software, we can use timers, and if we are interested in counting some external event which are occurring repetitively, then we can use counters or event counters. So, these event counters are used to count the events happening outside of the microcontroller. For example, if we are interested to measure the frequency of any input square wave, then we can use timer and counter both at the same time. Counter to count the number of periods or high to low transitions or low to high transitions, and timer is for 1 second delay. So, that if we can measure these two things, we can determine or we can represent the frequency, that is number of oscillations or number of signal changes from high to low or from low to high in 1 second. So, these are the use of timers and counters of 8051 microcontroller. Another important point is that both timer 0 and timer 1, these are the two timers available inside 8051. Both timers are 16-bit timers. 16-bit timers means we can handle 16-bit data, or we can count 16-bit number inside those timers. and both timers and counters are up timers or up counters. Like this statement means that if we are using device as a timer, and whatever the value we are loading into the timer register, this value is going to be incremented by 1 with every clock cycle that timer or microcontroller is receiving. And that's why we are saying that it is up timer, because the count value which is available inside the timer register is going to be incremented by 1. Similar is the case with counters. If we are counting any external event, then on every occurrence of that event, the value which is available inside the counter register is going to be incremented by 1. So we can say that in 8051 we are having up timer or up counters. And if we are going to deal with 16-bit numbers with 8051 microcontroller, which is a 8-bit microcontroller only, so it is not very difficult for us, because the manufacturers of 8051 has provided two separate registers. Both registers are 8-bit wide, and combining these two registers we can deal with the 16-bit numbers. These two registers are often termed as TH0 and TL0. These two registers are associated with timer 0, and TH1 and TL1, these two registers are associated with timer 1. Here you can see that TH0 and TL0 for timer 0, and the lower byte of the count value, or lower byte of the number, is stored in TL0, that is timer, and L stands for lower and 0 stands for timer 0. So it is timer 0 lower register, and this TH0 is timer 0 higher register. Here the MSB side byte is stored inside this register. The same situation is true with the registers of timer 1. These registers are TH1 and TL1. Another thing another thing is that when we are going to use the timers or counters with 8051, we need to define their functionality, or we need to define their mode, that in which mode or how we are intending to use these timers or counters with our microcontroller. So, to define the mode or to define the functionality of timer or counter device, we have a special function register with 8051, and this special function register is known as T mod register. So, T mod stands for timer mode register. So, here by writing 1 and 0 at certain situations or certain positions, we can define whether this device is going to act as a timer device, or this device is going to work as a counter device, and we can also define that how these timers or counters are going to be executed. So, here quickly see the structure of T mod register. This is the structure of T mod register. The MSB side is gate, then C oblique T bar, then M1 and M0. Here you can see that this register is divided into two equal parts. This is a 8-bit register. We can access this register as a whole at any moment of time, but to remember the functionality, it is very easy to understand this register is having some kind of symmetry. So, the lower 4 bits are basically used to configure the timer 0 device, and the upper 4 bits are used to configure the timer 1 device. So, if we are talking about timer 0 device, the first bit that is important is gate. Here in timer 1 also gate bit is here. The gate means how we are going to control our timers or counters. So, we can control our timer or counter in two possible ways. First way is to hardware triggered, like whenever we are providing any input signal to the microcontroller, our timer or our counter is going to be start. This is the hardware triggering of, or hardware based triggering or starting of timer and counter. The second possible way is to control or to start or off the timer counter by using software. Software means by using some instructions. So, we can start or stop the timer by using some software or some instructions in our program. This is the software control, And if we are intending to control or start or stop the timer by using some external signal which is being provided as input to the microcontroller, this thing is called as hardware control of timers and counters. Most often in our applications, we generally use the software control of timers and counters. So, if we want to control our timer by hardware, we have to write 1 at this gate bit position, and if we want to control our timer by software, then we will write 0 at our gate position, gate bit position. So, this is the description of gate bit in both cases for timer 1 and timer 0. The second bit in the series is C oblique T bar. C stands for counter and T stands for timer. And we can see that there is a bar on the top of T, that means this T is active low signal, and C, there is no bar above the C, that means this is active high. That this thing makes it simple to understand that if we are putting 1 at this bit position like C oblique T bar, that means we are enabling the counter, and if we are writing 0 at this bit position, that means we are enabling the timer device. So, if we are enabling timer device, we want to this device to act as a timer, then we can write 0 here, and if we are enabling this device as a counter, then we can write 1 here. Same situation is with timer 0. The same explanation for the timer 0 also holds true. The next two bits is M1 and M0. Here also these two bits are M1 and M0. These two bits basically signifies the mode of your timer and counter device. So, we can say that our timer or counter devices may work in 3 different modes: mode 0, mode 1 and mode 2. When we are saying that mode 0, that means here you can see the table on my screen, that M1 and M0, if both are 0, that means this is mode 0, and this is known as 13-bit timer or 13-bit counter mode. The important thing is, if we are configuring our timer in as a 13-bit timer, that means we can count only a 13-bit number. Okay. So, if we are having a 16-bit register with ourselves as a timer register, but we cannot go to the full range from 0000H to FFFFH, because this full range is required when we are this full range is applicable when we are working with 16-bit numbers. If we are working with mode 0, this is a 13-bit timer mode. That means we can count up to 13-bit numbers, that is 1FFFH. This is the highest limit of this 13-bit number. The another mode is 0, 1, that is also known as mode 1. If we are writing 0 at position M1 and 1 at position M0, that means we are configuring our timer as mode 1 timer, and mode 1 basically provides us the full length of the counting, that is 16-bit timer or counter device it is, and now we can count from 0000H to FFFFH. The interesting mode is mode 2, and if we are writing 1 at M1 and 0 at M0, that means we are configuring our timer as in mode 2. Mode 2 is 8-bit timer or counter mode with auto reload facility. So, what is this auto reload facility? Consider a situation that if we are working with the timers and we have loaded the timer with a value 1020H and we have started the timer. So, as these are up timers, then after every clock pulse this value is going to be incremented by 1. So, 1020 to 1021, then 1022, then 1023 and so on. This value will goes up to maximum number, that is FFFF. We are certainly considering the 16-bit operation of our timer. What will happen after FFFF if next clock pulse is coming? This value is again going to be incremented by 1. So, if we are adding FFFF with 1, then we will get again 0000 and 1 as a carry. So again our timer register value is going to become 0000H. This is the time when interrupt is supposed to be occur. And if interrupt has occurred, we are changing, we are doing some event or we are doing some useful task, and again we are starting the counting. But this time our counting is going to start from 0000H, and we were supposed to start counting from 1020H. So this is the problem. So every time when timer register overflows, or every time when this rollback is happening with the timer register, we need to reload the timer register with the appropriate value. So these are some additional lines required in our assembly language program. So to avoid these things, we can use timer in mode 2, where certainly the counting range is going to be short, because now we can count only on 8-bit numbers, and we can go from 00 to 255 in decimal number format. But there is no need to reload the counter register or timer register every time, because there are two registers, TH and TL. Whenever we are loading the timer register, that value is stored in another counterpart of that register, and every time when reload is occur, or every time when reload is required, the same value is being copied from another register to the main register. So this is the operation and the mode of timer and counters available inside 8051 microcontroller. The next thing is, we have configured the timers, and we have configured or we have enabled the interrupts, but to control the timers we are having another special function register, and that register is known as TCON register or timer control register. So if we are talking about timer control register, again it is a 8-bit register, and every bit signifies one specific task that this register can do. So starting from IT0, the interrupt 0 type control bit, and it is set or cleared by software to specify falling edge or low level triggered external interrupt. So here we are not considering the interrupts into our discussion. So this bit is of no use for of us at this particular time. But if we are dealing with external interrupts, then certainly we would like to discuss this IT0 bit more in detail. The same case is with IT1. This bit is related with external interrupt 1, and since in our discussion we are not including the external interrupts, so we are not going to discuss this bit in detail also. Oh sorry, IT0 is timer 0 interrupt 0 type control bit set or cleared by software to specify falling edge low level triggered external interrupt. And IE0 is external interrupt 0 edge flag set by CPU when the external interrupt edge is detected, cleared by CPU when the interrupt is processed. So the important thing is that whenever we want to start or stop timer, or start up or stop counter, we can use certain bits of these register, this register TCON register, and the bits which we are going to use are TR0 and TR1. TR0 is timer 0 bit and TR1 is timer 1 bit. TR0 is used to start or stop the timer 0, and TR1 is used to start or stop the timer 1. So whenever we are dealing with timers, to start the timer after the loading timer register and setting up the configuration in T mode and interrupts, we will start the timer by using by setting this TR0 bit, or we can start the timer 1 by setting this TR1 bit. If any moment in our program, if we are making this TR0 bit 0 or TR1 bit 0, that means we are turning off our timer in our application. These are the flags associated with the timers TF0 and TF1. TF1 is timer 1 overflow flag set by hardware when timer counter 1 overflows, and important thing is that it is also cleared by hardware as the processor vectors to the interrupt service routine. It's mean to say that whenever overflow or rollover condition is occurring, then our timer interrupt, our whenever the rollover condition is occurring, our interrupt is going to be occurred for the timer 0 or timer 1. And this interrupt is basically generated by the hardware itself. We don't need to do anything specific in our program. And whenever this interrupt is to be serviced, like our program control is being transferred to the particular interrupt vector address that is dedicated for timer 0, this flag is being cleared by the hardware itself. We don't need to do anything with this flag. Yes, if we want to monitor the operation of these timers, then we can basically monitor the status of these flags as well. So, this is the timer counter 0 register values. Here are some tables that I have taken from the data sheet of 8051 microcontroller provided by Intel. As a timer, if we are configuring timer 0 function 13-bit timer, then the control word or the T mode value, T mode register value is going to be 00H. And if we are configuring timer as a 16-bit timer, then the T mode value is going to be 01H. And here we are considering internal control or software control, like we are going to control or turn on and turn off the timer by using some instructions only. If we are controlling our timers by using some external signal, then these control words are going to be changed, like 08, 09, 0A and 0B. Similarly, the case is with the counter, and in case of counter, you can see here that 13-bit timer is available, 16-bit timer is available, 8-bit auto reload. These are the value. Easily you can see these values, or you can manipulate these values by using the timer T mod register configuration. Like here for internal control, it is written that 16-bit timer internal control 01H is required, and quickly see the T mod register. We are not talking about timer 1, this bit is 0, then this CT bar is 0, this M1 is 0, this is 0. So, overall this number has become 0 in hexadecimal, and here we are doing internal control, gate is 0, then we are using timer, then this bit is also 0, and we want to run in mode 1 because we are talking about 16-bit timers. So, we can write 0 1. So, this number will become 1H, and collectively I can say this 8-bit number will become 01H, and this is the answer. If we are doing internal control for 16-bit timer, the bit value is the T mod register value is 01H. Similar is the case with timer counter 1, only this time we are going to change the upper nibble of this T mod register, because we are basically taking timer 1 into our consideration. So, this is for this session, and in the next session we will see that how we can write some useful code and how we can debug that code, so that we can understand the interrupts and timers collectively, and in more practical behavior or practical situation we can use these concepts of timers and counters. Till then, stay safe, stay happy. Jai Hind.